In this video, we will work with stiffeners. I have already here open in XTTD and on stiffener panel, where I have already placed the traction boundary conditions and the displacement boundary conditions to constrain rigid body movements. So how do I create our stiffener panel from this? First thing that I will do is to create the first stiffener here at the central position. So to do that, I double click to select the sheet, right click here, add, I can add internal boundaries, cracks, I will add the stiffener. When I do that, I have here the place where I can select the exact geometry position. I click near the center, but it's never exactly 0, 0, which I have to choose then here, apply the changes, and accept. So that's it. We already have a stiffener here. But this stiffener was created with default properties for everything. So now we have to adjust that to what we want to have, okay? So let me change the properties. I double click on the stiffeners to select it, right click, properties. I don't want to change geometry because I've just done that. I will change the material properties first. By default, it is using A20-2040 aluminum. I will just grab from the database the A7075T6 aluminum. It already brought the correct properties. I'll just click OK. Next, I just go to properties again and I select cross-section. It is by default bringing the first frame it finds in the database. I will just come down here and select frame 10, which is heavier. I just click load and OK, and it is changed. Last, I come here and I have the attachment created as a fastened attachment. I could change here to bounded if that was what I wanted, but I want to use a fastened attachment. But I will change the rivet. So if I select here, it brings me what rivet I am using. Again, I will just look at the database and choose another one. I will choose this one here, load. And then I have the new rivet here. Something that happens is whenever I choose a rivet, it uses a multiplier to suggest a rivet pitch. In this case, it starts with this multiplier with the value 8. So as the diameter is 4, the pitch will be 32. Okay, I can change this to my liking, so I can change here to 6, for example, and it will calculate the next pitch, or I can change here to 30, for example, and it will calculate the multiplier. In the case, I will just use the suggested number 8, so the pitch becomes 32. I'll click OK, and then I'll get this message. What is it? Was it actually telling me here? It's telling me that it has adjusted the length of the stiffener, actually the half length, because that's what we input there, because the half length has to be an exact multiple of the pitch. That is because the generation of the mesh, and generally it is a small adjustment that does not change the size very much, but gets the stiffener ready for the analysis process. Just have to close this, and then I have the stiffener. I have one last adjustment that I have to make here. You'll notice here that there are forces applied to the extremities of the stiffeners. The aim of having these forces here is to satisfy a common requirement, at least in aerospace structures, that before I add a crack here, the sheet and the stiffeners both have the same strain. They have to be deforming uniformly. What you really add forces to the attachments is the crack, right? But it comes here again with a default value that we have to adjust. Let's look at the traction force here. So I come to boundary conditions change, and I can see that I have a traction of 200 megapascals applied. I just have to apply the same traction to the stiffener. So I'll come here, boundary condition change, and I will just change this to 200 both at the start point and at the end point. okay? In order to have the same strain, the actual load applied to the stiffener will have to be a bit different. Remember that the sheet is made of A20-2043. Well, I have not shown you that, but if I go here, properties of the sheet, not geometry, but properties, material properties, we see that we have the A20-2043. In the stiffeners, we have changed that to A70-70-56. So in order to have the same strength, the amount of load applied here is going to be a bit different, okay? But the XVTD takes care of that automatically. We'll verify if that is working later on. But with this, we'll have a stiffener placed here with everything that we want. Before I move further, I will just save this with another name. I will just place this with the name impact. Impact control. And you guess why I'm doing that, right? So I'll save. So now I have the first stiffener, and I have to create, do the sum to create 7 additional stiffeners, 3 to the right and 3 to the left. But that's what XTTD is made easy, because you can just select the stiffener here, and you see that I have new buttons in my toolbar here, and then I can just copy this stiffener and paste it somewhere else, and it will be pasted with exactly all properties that we have already changed. So I'll place it at 200. Then I have to do it again at X400. Then at X600. Then at minus 200. That's why it's very convenient to have the global axis exactly at the center of the external boundary. Then at minus 100. And then at minus 600. I'll just save this and notice. Here we have our complete stiffened panel. Let's verify that option that the sheet and the stiffeners without the crack will have the same strengths. So for that, let's just run one analysis here. And then we can look at the results for this stiffener and attachment line and verify that. So first thing I'll do, I'll just look at the attachment forces. And as expected, they are totally 0, right? You see that if I put here, they are not exactly 0. It's some microns here because XTD is actually calculating this, right? The solution of the system returns a value which is very, very close to 0. I can see this if I hide here the yield force. You can see that there are forces there, but you see they are very, very, very low, so it's virtually 0. The next thing to do that is always the philosophy. I never tweak anything. The results are exactly as the analysis code outputs. So that's very good so that you can really see what's going on with the numerical precision, for example. So I can look also to the deformation. And we see that we get 0 again. And if I just want to complete, I look at the stiffener stresses. And this is interesting because you see, it has a constant stress throughout, as expected, because there are no forces changing that situation here within the stiffener. But look at this is not exactly 200, you see? Why? Because of the difference in materials. XDTD has calculated the proper stress or load to be applied at the end point of the stiffener so that the strains would be the same. But because of the difference in material, the stresses in the stiffener, they are different, okay? So it's doing correctly. So I'll just cue this. I will also kill these analysis results, which I can do if I click here. You see, this is analysis and this is delete analysis. So I just come here, I will delete this first results and save this again. What I want to do now is to add a central crack here in the middle, and then run a propagation analysis. Then we can see what is happening, for example, with the stress intensity factors. Let me just double click here, add embedded crack. Then I have, as usual, the place to correct the geometry. I will just select 0, apply, and I have our crack. I will keep this default size, right? Initial size. You will have the crack here at the central position. I will save again, and we can now just run. I will run a crack propagation analysis. Let me just explain this here. The XCTD has the option, for example, in case the rigid material properties, they bring the stress strain curve for the rigid unknown, right? I can use industry formulas, or I can take other factors into consideration, like the difference actually these are industry formulas that translate the stiffeners, the fastener specific flexibility or stress strain curve into the joint stress strain curve. So they take into account the two sheets that are being connected by that, right? In this case, I'm just assuming my stress strain input is okay, so I'm using the direct input. And I will run a crack growth analysis. I want to have 25 increments of crack growth, and I will get up to 300 millimeters. I just click OK. It has already run, and I can now just have a look at what is happening with, for example, the stress intensity factors. And I'll hide with fracture toughness here. So we have the expected behavior that the stress intensity factors go up and then go down as the crack approaches and gets near the stiffeners, right? And then starts rising again. Let's have a look at what is happening with our stiffener and attachments. Let's look at the attachment forces, for example. And we can see that the attachment forces and the crack, remember, goes through the middle here. In the first rivets, each side of the crack, the forces here are exceeding the end limit for that rivets, right? So that this analysis is not feasible. We have to consider the plasticity here. So how do we do that? We just go back here and run the analysis again. But this time, instead of elastic, I just choose the attachment behavior to be plastic. Plastic is actually elastic plastic, okay? And I just click OK and run exactly the same analysis again. And just look at what's happening now with the attachment forces. And you see that XCTD has correctly determined that the loads here cannot go above the yield force for that material, and there is some accommodation. If I compare, the loads will be higher here to accommodate the force that has migrated from this to there. Let's have a look at the deformations to see if we don't have any situation where the deformation is excessive, and we don't. This is the deformation limit, and we are quite far from it, so there is no problem. And as a last thing, let's have a look at the attachments stress strain chart. And we can see that it's mainly in the elastic region, and then I have a few positions where I have plastic behavior. So this all looks fine. But no, remember, this is the stressing test factor for that other solution. How can we compare with the new one? And actually, to do this is very easy. I have here the chart for the first result set, which was the elastic analysis. I just click here. This means I want to compare two result sets for exactly this chart overlaid, one on top of each other. Then you ask me which case studies do you want to compare. I click all because it's this two here, the plastic and the elastic analysis, right? So I'll just click OK, and immediately I can see the two curves here. I'll just hide the fracture toughness so that we can see the difference, right? And we can see that when we took into account the plastic behavior, the stress intensity factors are higher because the stiffener is not as effective in constraining or and reducing the stress intensity factor, which is exactly what we would expect, correct? Okay, so with this, I think we have performed the analysis of our first stiffened panel. I will just save this. And what I want to do now is, what if I want this central stiffener to be broken? Because that's a common requirement, especially when you're doing residual strength analysis, right? So how do I do that in XBTD? But first thing I'll do, I'll just save this with another name. Instead of impact center, I will just put here broken center. Let's capitalize here just to. So I preserve the impact one because I want to compare the results from that case study with this one. Okay, so how do and here I will delete the results that I had previously here because I want this clean. How do I break the stiffener? I double click here, select the stiffener, and I just say I want to break the stiffener. At GTD, I'm just saying that it's going to adjust the size, and it has done that, okay? So if I click here again, I see that I have each stiffener, it is divided into pieces. We see that there is a bit of small difference here in the length of the stiffener, but that makes no difference, right? Because this is just a modeling stuff. But this is already there. I have the broken stiffener here. How now run the analysis again with exactly the same parameters, 25, 300. I run it with elastic, and obviously if that situation was not working for that, it will not work here as well. Let's look at the stress strain here for the central stiffener, and we can see that it is out of the linear range by quite a lot, right? So this analysis is useless. I will just delete it. And I will run this again, this time with the plastic, which is, as I said, elastic plastic. I'll just perform here. I have to put this again, 25, 300, and I run it again. If I now look at the behavior for this stiffener here of this stress strain curve, we have the expected behavior. This is because for these attachments, after as the crack grows, there is a relaxation here because this opens up and then the deformation reduces. But the stiffeners are already, the attachment points are already in plastic behavior, right? So they stay like that. But the deformation is not as it was before. Some of them go back here, you see. Let's see what is happening with this one. And we see that for this case, because for those there is relaxation as the crack grows, but not for this one. For this one, the situation just gets worse as the stiffeners move here. So this is the correct stress strain, and we see that we don't have anything, any position displacing beyond the limit value, so it looks okay. But I will anyway have a look at the attachment forces here. And we see that here there is the plasticity is much spreader than in the other case, because the loads are much higher because of the central stiffener broken, right? Another way we can look at this is just to click here and select to see an animation. An animation will show me what happens as the crack grows with each and every attachment position for each crack increment. You see? Let's pause here. You see that because of the central broken stiffener, even at the start of the crack grow, I already have plasticity here. As the crack continues to grow and approaches the stiffeners, probably these two stiffeners here, you see that more plasticity develops here, right? I like this because you can see exactly what is going on with the structure. If you're not interested in the animation, you can come here and look straight at this, which is the status by location. It will be by default the last iteration, and you see that we have the same information here, but a bit easier to visualize, actually. So, what I want to do now, I will kill all these genes. I now want to look at to compare the stress intensity factors for this. With the stress intensity factors, I can see the stress intensity factors the same way here. So I will just kill the fracture toughness and one of the, and I want to compare now what is happening with the stress intensity factor for this configuration with the broken stiffener and for the other configuration with the intact stiffener. Okay. In order to do that, I'll save this. And what I do is I just open the other case. So I will open the intact stiffener here. So now I have the two open here. And when I do that, I can come here and just compare results. You see, I have the options to compare the results side by side and overlay. We'll look at the two of them to see the difference. So first, I will look at the overlaid result. So which are the case studies and result sets I want to compare? You see that there are two here because for the intact, I have the elastic and the plastic. I will just compare the plastic with the plastic from the broken. I select them, I've just selected here which result sets from each case study I want to compare. And now in event to select which component type, which type of result I want to compare. So it's a crack tip result, a stress intensity factor. I want to compare in terms of a line chart. I use just the collected one because this is perfectly symmetrical, so I have to choose one, and I choose one, and I run that comparison for all the stages of crack growth. Then I just click OK, and then I have here the stress intensity factors for the two cases, and we can see that for the case of the broken stiffener, the stress intensity factors are very much higher, right? Something that we can do if we do any kind of parametric study, for example, every time I have this, I can see this percentage sign here. I can just to choose to look at the results percentage as a percentage of each other, right? So I will choose here and I will say that I want to look at the stress intensity factors for the broken stiffener case in relation to the stress intensity factors for the intact central stiffener case, both in the plastic version. And I'll just click OK, and I can immediately get the percentage difference. So for the small crack length, the smaller crack length, it's 120% more. And then it reduces as we have, get a range from the stiffener that is throwing load at the structure, right? But even in the end, it's around 60%, right? This is just a nice rule or make it easier to make comparisons. I can also use the delta here. If I do the same with the delta, I will just see the difference in terms of stress intensity factors, right? And not as a percentage. And as I told you, if I want to compare this side by side, I just do the same here. I choose the broken and the intact. Again, I choose to look at crack tip strip results, crack tip results, stress intensity factors, 2D line, crack tip 1, and L. And when I do that, it just puts the two charts on at the side of each other, right? I can here hide this, and I have the two charts here. But this is worse, actually. It's better to leave the fracture toughness here because then it gives us a better idea of what is happening here. And guys, with that, I hope I have given you a very good idea how to work with stiffeners in XDTD, how to copy and paste them. So you, from one stiffener, you create a complete stiffener panel, how to work with different analysis types, elastic, plastic, and how to generate results, how to break a stiffener, which is something that is very easy to do in XDTD, and how to compare and calculate results. With that, I will close this tutorial video. Thanks for watching.